So to begin to talk about quantum mechanics, we have to take a little visit to physics and understand what some of the properties of light. So light is a form of electromagnetic radiation. Electromagnetic, it's got electric fields and magnetic fields, and those oscillate, and they're perpendicular to each other. So you think of the one field is oscillating up and down, and the other field is oscillating side to side, and this energy travels through space. So in an electric field, we have an area where electrically charged particles are going to experience attraction or repulsion. In the magnetic field, magnetized particles will experience that force. So all electromagnetic waves move through space at the same constant speed. This is called the speed of light because it's how fast light moves. And it's pretty fast, right? 3 times 10 to the 8th meters per second. That's crazy fast, right? All light, all electromagnetic radiation travels at the same speed. Lots of other things are different about the different forms of it, but it all moves at the same speed. So here we have an illustration of electromagnetic radiation. So here we're drawing the electric field component as this oscillating field going up and down. And the magnetic component is going in and out of the plane. And together, they are moving in this direction at the speed of light. So it's too... I can't, try to do that with your hands. They're laughing at me. That's okay. I laugh at myself all the time. You can't do it, but you get the idea, right? Yeah. So light and sound are two different things, right? And they travel at different speeds. So I think we've all seen and heard lightning and thunder, right? You see the lightning strike somewhere, and then the sound comes later. The light and the sound were generated at the same time, but light travels 3 times 10 to the 8th meters per second. Sound is pretty slow. It only travels 340 meters per second. And so we get this lag between what we see and what we hear. And when the distance is a couple miles, that's a pretty significant lag. You can even observe this in like an auditorium or a stadium where you've got a really big marching band and the guys in the back, they can't go on what they're hearing. They have to watch the conductor because there's this lag. This happens at the swim meets too, timing the swim meets, and they always tell the timers, don't listen for the pistol shot, watch the light. Because if you wait for the sound, there goes a second or two, and that can be pretty important. So sound and light travel at different speeds. That's why you can, kind of count and estimate how far away the lightning strike was by the distance, the difference in time between when the sound and the light got to you. But all light is going to travel at that same speed. So we've got these waves, and we quantify them or characterize them. So what we call amplitude, the wave is pretty much a sine wave is what it is. So it goes up and down and up and down, and it goes through this middle point, and we just refer to that as the zero. So it's going up above and down below. And so the amplitude is how tall the peak is. And that's going to be consistent, and that's going to be the same as how deep the trough is. So it's going an amplitude above and an amplitude below this middle line. That is a measure of light intensity, how bright the light is. If the light is very bright, it has a larger amplitude. If it's dim, it has a smaller amplitude. The wavelength is the distance between one crest and the next crest, or between one trough and the next trough, stupid pointer, or between alternating nodes. These are called nodes where it crosses this middle line. So that's the wavelength. It's the length of a wave, and we use this, the Greek lambda, this is lowercase lambda. It looks a lot like an upside down y, upside down lowercase y. So you'll need to know that letter. So here we have 3 different waves. These waves all have the same amplitude, the same height, right? They are all the same intensity. They're all moving at the same speed, but here the wavelength is different. This one has a long wavelength, kind of a medium, and a short wavelength. The wavelength of the light determines what color it is. So if we see red, yellow, blue, we perceive those as different colors because the wavelengths are different. When you have a dim light, it's going to have a low amplitude, and a bright light is going to have a high amplitude. Here, these would be the same color, but just one's brighter than the other. Yeah.
So for someone who's colorblind, is it just because they see the wavelengths?
That's a good question. So what about color blindness? Well, what about color vision in general? Or vision? Have you ever thought about what exactly is seeing something? Yeah. Mind blown number 2. Great. Why'd you have to ask that question? You have molecules in your eyes that interact with this electromagnetic radiation coming into your eye. And they undergo some changes that send signals to your brain that your brain interprets as vision. So there are rods and cones in your eye, and there are 3 different kinds of, I think it's the rods that are 3 different kinds for color vision. And so someone who has a color vision deficiency, some of their rods don't work the same way as most people's do. And the type of deficiency can vary tremendously. It's very rare, but there are people who really don't see any color at all. Most people who are colorblind do see some color. They just don't perceive the colors the same way that we do. Interestingly, of my 5 sons, 4 of them have some color deficiency. So we have some interesting arguments about what color is that hat. It's navy blue, but they think it's purple. You know, the house that we lived in back when, it was gray, but he says it's blue. You know, he sees the colors differently. Do you have a question?
Yeah, in the sense of the wavelength also attributes to the amount of heat something is, because you know how blue is like the hottest. So.
Yeah, it does. It does also affect the amount of energy that the light carries, and we'll get to that in a minute. Anybody else have any questions? Yeah.
If he sees your house as blue, but he's always seeing the house as blue, then wouldn't he just always associate that because you always call the house gray?
Mm-hmm. Well, that's a really good question. See, the thing is, the blue and the gray look the same to him. Yeah. Another interesting thing that happened, he was helping at VBS, Vacation Bible School. He was one of the rec leaders, and they were playing this game where they took a whole bunch of colored paper clips and threw them in the grass. And then the kids had to pick them up. He couldn't see the red paper clips in the grass because they looked the same color to him.
It's a terrible story.
Right? It's a terrible story. It's very strange. I have an uncle who's colorblind, and in the spring, the grass is the same color as the fire trucks. But later in the summer, grass changes color as the new grass is a more yellowy green. Then later in the summer, they're not the same color.
Did you see the green ones?
He could see the green ones. He could see the green ones in the grass. I mean, I don't know that it was any better than we can see the green ones in the grass, but he couldn't see the red ones. They just blended in. They happen to be the same color to him. So, yeah, you think about different perceptions, and then you think, well, maybe that's why some people hate the color orange, and why other people like the color orange, because it doesn't look the same to everybody. And then how do you test that? Yeah. Okay, let's move on then, huh? Characterizing waves. Okay, so we talked about amplitude, and we talked about wavelength, and they're all moving at the same speed. What speed? The speed of light. Okay? Okay, I'm just going to tell you, there is a question on a pre-lab coming up that is going to try to trick you on that. Okay? All electromagnetic radiation travels at the same speed, the speed of light. Okay? That's your big hint. So frequency is another characteristic of waves. And that is unfortunately given this Greek letter. That is not a V. It's not a lowercase v. That is new. It's a Greek letter. So when I write it, yeah, right? Because that doesn't look at all like that. The first side is straight and the second side has a little curve in it. You kind of have to use context to determine is it V or nu. It's the frequency. The frequency is the number of waves that pass a given point in a certain period of time. So another way to think, to help us understand waves is we've been to the ocean, most of us, or we have seen movies or TV shows or something. And you know the waves, they keep rolling in, right? They just keep coming and coming. So if you're standing there in the surf, the frequency would be counting how many waves hit your legs, say, in 5 minutes. You would take the number of waves, divide by the time, and that would be the frequency. Okay, so it's how many things happen in a period of time. The number of waves, the number of cycles. Frequency is used in other areas as well. We talk about electric current. It has a frequency because it has an oscillation as well. And so 60 hertz or 30 hertz, there's a refresh rate on your computer screen, and that's in hertz. I guess, oh yeah, there's the word. Hertz, not the rental car company. Abbreviated capital H, lowercase z, and hertz is the same as how many cycles per second, how many events in 1 second. So it can also be s to the -1. So we say 1 hertz is 1 per second. 1 what? 1 cycle. 1 cycle per second. So the total energy of the wave is proportional to the amplitude, how tall it is, but also to the frequency. So if you think of standing in the surf, if the waves that are hitting you are really big waves, you're going to feel it, right? You're going to feel the energy of that water running into you. And then if they're coming really frequently, you're going to really take a pounding, right? Whereas if you're standing there and you've just got really low amplitude waves just coming every once in a while, that's just not really going to impact you very much. So high amplitude, high frequency, more energy. Does that make sense? There's a relationship between wavelength and frequency because for electromagnetic radiation, all the waves are traveling at what speed? The speed of light, right? So if they're all coming at the same speed, if you have a shorter wavelength, they're going to hit you more frequently. If you have a longer wavelength, they're going to hit you less frequently. So let's draw a bad picture here. There's a really good reason I didn't go into art. I'm good at Pictionary, but I'm not an artist. So if we think of this wave versus this wave. So they're traveling at the same speed, and you're going to count how many peaks pass in a given amount of time. Well, this one, you're going to get 3 peaks in that time, and this one you're going to get 1, 2, 3, 4, 5, 6 peaks, 6.5 peaks. So this is higher frequency. This is lower frequency. Well, how do the wavelengths compare? This is the wavelength right there. And here's the wavelength. So short wavelength, high frequency. Long wavelength, low frequency. And this is the relationship. The frequency equals the speed of light divided by the wavelength. So it's an inverse relationship. If we make the wavelength larger, the frequency is smaller because c is constant, the speed of light. Any questions? Color. So the color of light is determined by its wavelength. And since the wavelength is related to the frequency, you can also say it's depends on the frequency of the light. So what we perceive as white light, which is like the light that comes from the sun or from an incandescent light bulb, is a mixture of all the colors. It's a spectrum. It's a continuous spectrum. There's all the different colors present together. So if you take white light and pass it through a prism, what happens is the light gets bent by the sides of the prism, and the amount of bending depends on the wavelength of the light. And so you pass white light through a prism, and it separates the light by wavelengths. This is what's happening when you see a rainbow in the sky, when you see... You can see, this is just random noise in the back room there. You can see a rainbow in the front yard when the sprinklers are on sometimes. When the light hits the chandelier just right, it puts little rainbows all over the place, right? That's light passing through a prism, and in passing through that prism, it gets separated into the wavelengths, different wavelengths. They're always separated in the same way. At one end that gets bent less is red. There's red, orange, yellow, green, blue, indigo, and violet. Okay, so those are the order. Red, orange, yellow, green, blue, indigo, violet. So one way to remember that is Roy G. Biv. As, you know, like somebody's weird name. Roy G. Biv. You could be thankful that's not your name. Red, orange, yellow, green, blue, indigo, violet. Sometimes you'll see a drawing that a child has made of a rainbow, and you're like, well, yeah, that's really pretty, but there's something's not quite right. Because they mess up the colors, right? They just put the colors in random order. And yes, it's curved, and yes, it's got all the colors, but they're not arranged in the correct order. So our mind recognizes, hey, wait a minute, that's not right, but we don't necessarily consciously observe what's going on with that. But it's always going to be in the same order. When we observe something to have a particular color, like here this woman is wearing a red shirt. Why does the shirt look red to us? Well, the shirt is absorbing most of the wavelengths of light, but it's reflecting the red light. So we see the red light. You know, you got a blue backpack. That's blue because it's reflecting the blue light. Now, is it just reflecting one wavelength of light? No, it's reflecting selected wavelengths, and that's why we get all these different colors, is because you have different combinations of wavelengths that get reflected to you. Okay. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency. You knew there were equations coming in math, right? It's inevitable. Well, we have that equation. The frequency equals the speed of light divided by the wavelength. This one's relatively straightforward. It's saying calculate the frequency. Well, frequency equals the speed of light divided by the wavelength. Well, we know the speed of light is 3.00 times 10 to the 8th meters per second. Let's not write that as a slash fraction, but a horizontal fraction, but like a vertical fraction. The speed of light, 3.800 times 10 to the 8th meters per second. If you need that, I'll give that to you in the useful information table on the exam, but you might end up just kind of memorizing it. And so then we're going to divide by the wavelength. So the wavelength is 515 nanometers. It's really important to put your units in your equations, because you can't just take 3 times 10 to the 8th and divide by 515 and say, there's the frequency. Well, that is the frequency, but what are the units on it? They're whacked out. We have to get the units correct. So I've got meters up here, and I've got nanometers down there. Those are not going to cancel out. So we need to convert nanometers into meters. This is the easiest thing to do. So erase nanometers. What does the prefix nano mean? 9. Minus 9, right? 10 to the minus 9. So instead of nano, I'm going to just write what it means. 10 to the minus 9 meters. Right? This is equal to the prefix nano. That's the easiest way to do the conversions. So then you just get your calculator out, and you've got 3EE8 divided by 515 EE minus 9. Yeah, that's not proper scientific notation. Your calculator's fine with it. And you get a mass, of course. Each of these numbers has 3 significant figures. So my answer should have 3 significant figures, 5.82. Write down 2 extras just for grins. And times 10 to the 14. And then the unit, the meters cancel out, and so I have a unit of 1 over seconds. That seems like a strange unit, but that is the frequency unit. So that can be written as s to the minus 1 or hertz, Hz. So 5.83 times 10 to the 14th per second, or 5.83 times 10 to the 14th hertz. Now what I saw on the exam was 5.83 E14. Okay, I know what that means. That's what your calculator's showing you, but this is calculator language. And you need to convert it to human math language. So please don't use that form. Any questions? So visible light, the light we can see, is part of the entire electromagnetic spectrum. It's actually a really tiny part. There are shorter wavelength forms of light, shorter wavelength, higher frequency. That has higher energy. And there are longer ones. So radio waves are electromagnetic radiation. The same kind of thing as visible light, but they're just much lower in energy. Gamma rays are the highest energy electromagnetic radiation. We can't see gamma rays or radio waves because our eyes, the cells in our eyes that give us vision, don't interact with, they don't give us the correct source of signals for those wavelengths. High energy electromagnetic radiation can be very dangerous. It can damage biological molecules. It's called ionizing radiation. It makes ions out of molecules and atoms that should not be ions. And so it messes up the chemical reactions that are occurring that sustain life. Okay, so here is a picture, and this is a typical way to show the electromagnetic spectrum, and it is also often misunderstood by students. So up here we have a scale showing the frequency, nu, in hertz. So this is 10,000 per second, and this is 10 to the 24th per second. And on this scale, we're looking at wavelength in meters, so lambda in meters. And so this is long wavelength, 10 to the 5th meters, a wave that is like miles long, right? And this is crazy short, 10 to the minus 15. Right in this part, this is the visible light. It encompasses this little tiny part right in here. Let's see if I can. So it's this part right here. That's all. This little tiny piece. Now, that is, really small. It's hard to see. And visible light is really, really important to us, so we want to be able to see the different wavelengths and stuff. So what we're doing here is this part here is zoomed in on this little tiny part, okay? So here we've got wavelength shown in nanometers because it's a more convenient unit. Violet light, 400 nanometers. red light 750 nanometers, and in between we've got our rainbow, Roy G. Biv. So the thing that happens is students will see red over here and they'll say, oh, the wavelength is 10 to the 5th meters. Or they'll say, oh, this one is 10 to the minus 15th. No, this is zoomed in on this tiny little piece. Okay, so try to avoid that mistake. So we've got the visible light. You do not need to memorize exactly where these transitions are, but I want you to understand the order of them. So here we've got visible light, and I use that sort of as a reference point. So Roy G. Biv starts with red, goes to violet, just like we read, left to right. Over here, past violet is ultraviolet, right? Like ultralord, superviolet, right? It's past violet. And that is, can you get a sunburn from ultraviolet light? Yeah, that's the component of sunlight that gives you a sunburn, right? So that's got more energy than visible light. You can't get a sunburn from the fluorescent lights. So this is more energy. So we're going up higher energy, and then there's X-rays. X-rays are used, to take pictures of your broken hand, etc. And then there's gamma rays. Gamma rays have uses, but they also can be extremely destructive, and they can kill you. So we're going up in energy. On the other end, down here, below red is infrared. Below red. So there's infrared, and then there's microwaves, and then way down here there's radio waves. Now, microwaves, you might think, well, those must have a lot of energy because they make the water hot, they make the food hot in the microwave. Actually, they only do that because they interact very well with water molecules. It's really just the water molecules that get agitated when they're exposed to microwaves. That's why the microwave itself isn't hot. It's just the water that was in the microwave. But you should know the order here, okay? In your textbook, there's descriptions about the other kinds of light here. You should read those. I'm not going to read them to you in lecture. So we can separate light into different wavelengths using a prism. If you have white light, like comes from the sun, and you separate it, you're going to get a continuous spectrum or a rainbow, because there's all these different frequencies, different wavelengths present in that light. This is me, and that's my daughter. I used to use the book out of the picture out of the book, but then went to the Jet Propulsion Lab that NASA has down in LA, and they had this cool camera there. So I'm like, I'll take a picture of that and use this instead. So our eyes cannot see infrared light. Infrared light is the light that is given off by warm objects. The warmer something is, the more infrared light it gives off. So infrared is used for thermal imaging, seeing heat, or we also call it night vision. So you can see, not with your eyes, but with a special kind of camera where the things are warmer and cooler. And so this is regular visible light, and this is infrared. And so you can see our exposed skin is red, that's indicating warmer, and the background here is cold, that's blue. So they can use these to see in the dark. You get somebody hiding in the woods because they robbed the bank, and you get out the night scope and you can see them because there's this warm place, right? High energy radiation can be used. It's damaging to cells, but we can take advantage of that and use it to kill cancerous cells. So unfortunately, it's also going to kill the healthy cells or damage the healthy cells that it has to go through. So, if you have a brain tumor, you can't just cut into the brain and remove that. You have horrible consequences, of brain damage. So how do you get rid of the tumor? Well, you can send radiation from multiple directions, all focused on the tumor. So this beam is going to do some damage to the healthy tissue it goes through. And this one, they're going to do a little bit of damage to all this surrounding tissue, but because they're all hitting the same place, they're going to do a heck of a lot of damage to the tumor. And so you can maximize damage to the bad cells and minimize damage to the healthy cells. And that's radiation therapy for cancer. Okay, so waves. Waves can interact with each other, and it's called interference. So you can have constructive interference or destructive interference. Constructive interference builds the waves up. It makes them stronger, larger. This is when the waves react and they are in phase. So here, these two waves are in phase, meaning their peaks are lined up and their troughs are lined up. So when those two waves interact, they essentially add together. We still have the same frequency and wavelength, but the amplitude is much larger now. It's like being on a trampoline, and if you bounce just right, you can send the other person sky high, especially if they're a little smaller than you, right? And if you bounce the opposite, then nobody's like moving. That's the destructive interference, where the waves are out of phase. And you add these together, and they cancel each other out. And this is the principle behind noise-canceling headphones. They take the sound that comes in and shift it over half of a wavelength and send it back to your ears, and so then the sound waves cancel each other out.
I didn't know like the frequency of outside.
It just measures it. It's electronic, and it takes it in and it just shifts it. Yeah, it's pretty cool. So constructive and destructive interference. Another thing that can happen is called diffraction. So you've got traveling waves, and they encounter an obstacle or an opening in a barrier where that obstacle or the opening is about the same size as the wavelengths. Then it's going to cause the waves to bend around them. So waves will do this, but traveling particles do not do this. Okay? If you hit a tennis ball through a slit, it doesn't cause the tennis ball to bend if it doesn't touch the edges, right? If you hit it past a post, it's not going to cause it to bend. But if you send a wave through a slit, it'll cause it to bend. So waves and particles behave differently. So this diffraction that we see is a characteristic of all light waves. So all light waves do this diffraction thing. So this is what I'm talking about. So you've got a wave coming up to this barrier. And as it hits this barrier and some of it goes through, what we see is that the waves that come through are now curved. They're diffracted. If we throw particles at the same opening, some of the particles are going to go through. Their path will be unchanged. They just shoot right through. And others are going to hit the barrier and just stop. We can see this happen with water waves. That's a lot easier to observe than light waves, right? Because the light waves are too tiny, we can't see them. So I have another YouTube video here. This is one of my favorites. I'm going to talk about this real quick, and then we'll watch the video, and then I'll explain it again, and hopefully it'll make a little more sense. So here we have a light source. And since this is a single source of light, all of the wavelengths line up together. So you have wavelength, the wave hitting over here and the wave hitting over there. And as it goes through this slit, it gets diffracted. And this light gets diffracted. And then as these waves run into each other, they're going to interfere with each other. There's going to be some constructive interference and some destructive interference. And so over here, what we're going to observe is an area of high wave and low wave, where there's, if this is light. And so over here, we're going to see dark spots where the waves cancel each other out, and we're going to see bright spots where they intensify each other, constructive and destructive interference. And you can measure the wavelengths, and you can measure the distances here, and you can do all sorts of cool calculations that we're not going to do. So let's watch this video. And I'm going to dim the lights for this one.
What is light?
What is light? What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light, red light?
Colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today. Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Herring, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box, two bright bands.
Two little lines.
Man,
Yeah.
I think it'll be one line for two.
I'd be expecting the whole busted up.
That'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Oh, there's one in the middle strongest, two either side.
The two on the outside are multicolored, the one in the middle is just white.
And kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
Well, all we're doing is we're putting a light through two very narrow slits side by side. How does this make any sense?
There's some kind of principle involved there. The average person's not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern.
See that?
This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere, and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the
And
same
then they go
pattern.
and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, then a bright spot, then a dark spot, then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
That's
that's
because
exactly
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So,
between red
there's
and
so
blue.
that red bin over there, the green part, is just, I'm seeing
It's a
that, it's
different-
just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, you know, thanks, man.
Hey, thank you.
I have been enlightened, literally.
So that's one of my favorites. I love that guy with the rugby shirt. Oh my God. You just never know what you're going to run into on YouTube. Let's get the lights. Question?
So can electrons behave as wavelengths and particles at the same time?
Yes. Electrons can behave as waves and as particles at the same time. So let's keep talking about the waves for a minute. So we saw with the ripples, and I like that because you can so clearly see here are these waves, and then they even highlight, using video technology, the interactions. So you've got 2 sources of waves, and as they come together, we've got constructive and then destructive interference and constructive interference. And so what we saw in that box was bright spot in the middle, and then dark and bright and dark and bright. Does that make sense? So waves do this. This is called diffraction, and you just have to have these slits to be similar in spacing to the wavelengths of the light, but it'll work with any electromagnetic radiation. Anybody have any questions? Yeah.
So when, like, they have the dots and the rainbows, why was it, like, the orgy bib and then it was switched and then it went back?
Was it switched?
Because, like, when you see a double rainbow, it's, like, mirrored.
Actually, it isn't. No. A double rainbow is going to have this same order of colors. Now, on that double slit experiment, the red is bent the least and the blue is bent the most. And so on the slit, on the interference pattern, what you're going to see here is the order is going to be left to right, one thing here and the reverse there, because the more diffracted will be on the outside and the less diffracted will be on the inside. But in a rainbow, it's just happening the same. Yeah. Anybody else have any questions? So light is a wave. We're all accepting of that. Light is also a particle. So it was observed that many metals will emit electrons when a light shines on their surface. It's called the photoelectric effect. So photo meaning light, electric referring to the electrons. And classic wave theory attributed this effect to the energy of the light being transferred to the electron. And then when the electron had enough energy, it would get emitted. And with this theory, only the intensity, the amplitude of the light would affect the emission of the electrons. the frequency wouldn't matter, it's just the amplitude, it's just the amount of energy. So this idea predicts that if you used a dim light, there'd be a lag time before any electrons were emitted, because it would take a while for the electrons to absorb enough energy to leave the surface of the metal. Here's an illustration of a photoelectric apparatus. So here we have the metal surface, and light hits the metal surface, and the energy of the light causes electrons to be emitted. This is done in an evacuated chamber, and we've got an electrode over here that attracts the electrons, and then we've got a detector so that we can measure the electrons as they come off. So light comes in, and we get an electric current coming out. So experimental observations show this to happen. So here we have a graph, rate of electron ejection, so how many electrons are being ejected, versus the frequency of light. Classic wave theory says, well, the frequency doesn't matter, it's just the amplitude. So we've got lower intensity and higher intensity light. And so at low frequencies, it didn't matter how intense the light was or how dim, no ejection of electrons. You increase the frequency and you get to this magic point here, and all of a sudden, bang, it starts to emit electrons. Now, the number of electrons that get emitted per unit time is going to be lower for the lower intensity and higher for the higher intensity, but they're both going to start happening at the same time. And there's no lag time. You hit it with high enough frequency light, and it just immediately starts emitting electrons. So that doesn't work with the idea that they're just gradually absorbing energy from the light. Einstein proposed that light energy was delivered to the atoms and to the electrons in packets. So that's a little bit like having a piece of milk, right? How do you have a piece of a liquid? It doesn't really make much sense. A piece of milk, a piece of light, that doesn't make much sense either. A packet of light. So a packet of light is called a quantum or a photon. I'm sure you've heard the word photon. They make torpedoes out of them in science fiction movies. Fire the photon torpedoes, right? Those are light energy. The energy of this piece of light, E, the energy of the photon is directly proportional to its frequency. So higher frequency, higher energy. You think about standing on the beach and the waves coming at you faster. You're going to feel the impact of that more. That's more energy being directed at you. High frequency, high energy. That is then inversely proportional to the wavelength, as we saw that from, well, I'll just write it out here again. We use this one, E equals, no, sorry, nu equals C over lambda. The wavelength and the frequency are inversely proportional. So the energy is proportional to the frequency and inversely proportional to the wavelength. So we can say that E, the energy, equals a constant times the frequency, or E equals H, that constant, times the speed of light over the wavelength, because that's what nu is. This constant, H, is called Planck's constant. It's named after a scientist. And this is its value, 6.626 times 10 to the minus 34 joule times seconds. You don't have to memorize that. I'll give that one to you, okay? So we can calculate the amount of energy per photon. We can calculate how many photons are coming in a certain amount of energy, etc. So we could do a problem like this. This requires some critical thinking. So we've got a 100-watt light bulb, radiates energy at a rate of 100 joules per second. The watt is a unit of power or energy over time. The watt is defined as 1 joule per second. So 100 watts is the same as 100 joules per second. If all the light that's emitted by that light bulb has a wavelength of 525 nanometers, how many photons are emitted per second? And assume that there's 3 sig figs. Well, what do we have here? Let's just see what we can do with this. So we've got 100 joules per second, and we have a wavelength of 525 nanometers, and we know the speed of light, 3.00 times 10 to the 8th meters per second. So what can we do with this? We want to know how many photons are emitted in a second. Well, we know there's 100 joules in a second. So if we knew the energy of one photon, then we could find out how many photons it would take to give us 100 joules. So we're going to need the energy of a photon. That was the equation we just got on the previous slide, E equals hc over lambda. So we need to know what h is. Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. So h is a constant, c is a constant, and then lambda is the wavelength of light. So we can calculate the energy of one photon. It's based on its wavelength. So we've got Planck's constant, 6.626 times 10 to the minus 34. Joules times seconds. Units are very important. And then we've got 3.00 times 10 to the 8th meters per second. And then we need to divide this by the wavelength. The wavelength was given to us in nanometers, but we've got meters up here. So let's do that same little trick. Instead of writing the prefix nano, we're going to write what nano means. Nano means 10 to the minus 9. So this is 525 times 10 to the minus 9 meters. And let's see how the units work out. Well, we have meter and meter, so those are going to cancel. And here we have seconds, and this is seconds in the denominator, so those are going to cancel out. And this is going to give us a value in joules, which is the energy of one photon. So 6.626 EE minus 34 times 3 EE 8 divided by 525 EE minus 9. And we're going to get 3.7862 times 10 to the minus 19 joules. That's the energy of one photon. One photon of light with this wavelength. They're asking us how many photons are emitted per second. Well, it's 100 joules per second. One photon is this many joules. We can convert joules to photons. So 100 joules per second. I want to convert joules into photons. So one photon is 3.7862 times 10 to the minus 19 joules. The joules cancel out. Now I have a unit of photons per second. I'm going to round this to three significant figures because that's what it tells me to do. 2.64 times 10 to the 20th photons per second. That's a lot of photons. Photons are tiny. 100-watt light bulb, that's light you can see. That's going to be a nice bright light, right? It's got to be a lot of photons. Anybody have any questions? Okay, here's one that doesn't involve any calculations. So maybe you'll like this one a little better. Arrange these three colors, red, green, and blue, in order of increasing wavelength, increasing frequency, increasing energy per photon. This is something that will show up on the next exam. So how do you do this? Well, you can memorize stuff, but I don't think that works very well. Let's think it out. So I'm going to show you how I would do this. Okay, so what I'm going to do is I'm going to draw just a rough, ugly electromagnetic spectrum. So there's this line here, right? And in the middle here, we've got our visible light. And the visible light goes Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet. And then, so violet is on this side. So where is ultraviolet light? It's next to violet. So here's our UV light. And where's infrared? It's next to red. So this is IR, or infrared light. So this is light like you'd get from a heat lamp. You ever go to a motel and they have those heat lamps in the bathroom to warm the bathroom up for you? And it kind of glows a little bit. It's a little bit reddish, but it doesn't give off much light, but it gives off a heck of a lot of heat. Right? It's giving off infrared light. UV light, we know that's what causes a sunburn. Which has more energy? Which is going to cause damage? The UV. So this is higher in energy. So this side is high energy. And the other side must be low energy. See how I figured that out? I just think it through, because I can't remember which is higher or lower. Just don't do that. Okay, so if we're looking at energy per photon, and they're asking us about green, blue, and red. Order of increasing. I don't know, they don't seem to teach this in schools. Students have the worst time with this. If you're supposed to put something in order of increasing, that means you put the smallest one first, and then the next biggest one, and the biggest one comes last. Okay, that's order of increasing. So we want to find the lowest energy of those three colors. Which is it? Red. This is the low energy side. So increasing energy, red is the lowest. And I like to use the greater than or less than signs just to make it even more clear. And sometimes I'll get questions, well, I don't remember which side is greater and which side is less. Okay. This side is big, and that side is little. That's how I remember it. The little side goes to the little thing. The big, wide open side goes to the bigger thing. Okay. So what's next? So here's red. What's next? Green, and then blue. Okay. This isn't hard. It's just people get it mixed up. Okay, so there we did one. You don't have to do them in order. So now we've got frequency and wavelength. So it's like, okay, how do we do this? It's hard to remember which is which because one's upside down of the other, right? So then I'm going to think about, okay, here's my funny little person. Oops, his leg's not the same length. And he's standing at the beach. And these waves, all of these forms of light travel at the same speed, right? So which one's going to hit him more frequently? The top one, right? He's going to feel like he got a pounding, right? More force, more energy, right? So this one's higher energy. It looks higher energy, doesn't it? This one looks all slow, and this one looks like, crazy. Right? So this is high energy, that's low energy. Is this short wavelength or long wavelength? This one's shorter, right? Because this is our wavelength right here. And this is our wavelength down here. So this is short wavelength. Short wavelength is higher energy. So I'm going to label that over here. So this is short wavelength. And this is long wavelength. So we can order these by wavelength. We want to go in order of increasing. So we want the shortest first, and then the middle, and then the longest. Which one's shortest? Blue. So blue is the shortest, and then green, and then red. Right? Because this is going from short to long. Blue, green, red. So frequency. Maybe you can remember that frequency and wavelength are opposite. And so then to do the frequency, you just take this order and make it backwards. Or you can look at this and say, well, which one of these is going to hit me more frequently, more often? This is going to be high frequency, and this is going to be low frequency. So this is high frequency, and this one's going to be low frequency. So the order for frequency and wavelength are just going to be opposite. You're never going to have a situation where green is going to be the highest or lowest instead of red or blue. Green's always going to be in the middle of those two. Any questions? Yeah. So you should be able to think this through. Okay? Just got a couple ideas, draw yourself some pictures, think about for a minute. Okay, how much is left in this section? Oh, okay, 3 slides, we're going to do it. We did that, okay. Ejected electrons. So we were talking about the photoelectric effect where the light energy hits the metal and ejects electrons. So light can behave as a particle. One photon at that threshold frequency, that magic frequency, has just enough energy to dislodge the electron. And I think this is phi, I forget. But that's what we use for the binding energy of the electron. Why don't the electrons just fly off all by themselves? Because they're essentially glued to the metal. They're held by some force, some energy. So this is the amount of energy that holds the electrons, that binds them. If we send higher frequency photons with more energy than the binding energy, the electron is going to break its bonds, get away, and it's also going to have more energy when it escapes. So it's going to go off faster. So the excess energy becomes kinetic energy of the ejected electron. So the kinetic energy of that electron that's given off is the energy of the photon minus the energy of the binding. So the photon's energy is h nu, and the binding energy is phi. Okay, so that probably didn't make a lot of sense. So let's think about a child going to Disneyland, right? So you need money to go to Disneyland, right? It costs, what does it even cost now to get in for one day? Like $5 million? Yeah. Let's call it 100. So $100 just to get in to Disneyland, right? That's the threshold frequency, the binding energy. The electron needs this certain amount just to get in. What if you have $75? Will they let you in for 3/4 of a day? No. It's you have enough or you don't. You get in or you stay out. There's no middle, right? So the electron, if it gets a photon coming at it that doesn't have enough energy, like $75, nothing's going to happen. If it gets one that has $100, which is just the price needed to get into Disneyland, then the electron can go to Disneyland. What if the electron gets a photon with $200? Can he go to Disneyland? Yeah. He pays his $100, he goes into Disneyland. What's he going to do with the rest of that money? He's going to blow it on food and souvenirs, right? Yeah, stupid stuff. So the electron has to get a certain amount of energy, a packet of energy, this photon, with a certain amount of energy to get away from the metal. Anything extra goes into kinetic energy. It's just going to be able to move faster, have more fun at Disneyland. Does that make sense?
Is the binding energy determined by the atom that it's in?
Yeah, the binding energy will be affected by what kind of metal it is. It might also be affected by the temperature and several different things. But we can simplify things and say, okay, we're just looking at one set of conditions. And so for this example, we have a particular binding energy. So let's think about this. Suppose that a metal will eject electrons from its surface when it is struck by yellow light. What will happen if it is struck with ultraviolet light? Well, what determines whether the electrons will be ejected or not? The energy of the light, right? Which is higher in energy, ultraviolet light, UV light, or yellow light? Ultraviolet. Ultraviolet light will give you a sunburn. Yellow light will not. It makes me look like I've been ill for weeks, but it won't give me a sunburn. So yellow light is the minimum amount of energy needed for this metal to eject electrons. If you give it something that has more energy, what's going to happen? No electrons ejected. Electrons would be ejected, but they'd have the same kinetic energy as those ejected by yellow light. Electrons would be ejected, they would have greater kinetic energy. Electrons would be ejected, but they'd have lower kinetic energy. C. Electrons are going to be ejected, but they're going to have more kinetic energy. The UV light is like you give the kid the $100 needed to get into Disneyland and then some extra. So when he gets through the gate, the binding energy, then he has more energy, more money to go do stuff with. So you should be able to think about a question like that. So we've talked about light as waves. We've talked about light as particles. It's called the wave-particle duality of light. So like electrons and other absolutely small things, light can behave. It can be two things at the same time. But when you observe it, you force it to behave like one thing or another. It can't act as a wave and a particle at the same time when we're observing its behavior. I'll leave you with that.